Good evening, everybody. Welcome to the June instalment of the IMechE Switzerland events programme. Tonight we have a presentation from Farrat Isolevel on controlling vibration and chatter within the strip and sheet metal manufacturing industries. A little introduction to Farrat. They are a 60-year history within industrial vibration control, although the last 5 years have particularly have changed gear in the capabilities of the company. And tonight we're presenting a combination of the rich experience from the decades of work in the industry, combined with the young technology-driven approach to solving today's problems in industry, all in the interest of supporting customers to improve OEE, ultimately profits, but also the working environment of the employees within the factories. So it's in two parts. The first is by Jacob McCormick, application engineer with Farrat. He's supported by Yusuf Benhafsi, who is a principal application engineer. And then the second part, more focusing on presses, is by Florian Cabaret. So without further ado, if I just pass over to you, Jacob, and yeah, take it away.
Great. Thanks, Oliver. Hi, everyone. Yes, so as Oliver mentioned, this is going to be a two-part presentation. It's on controlling vibration and chatter to improve output in strip and sheet metal manufacturing. I'm going to be presenting part one, and my colleague Florian will be presenting part two. So part one is going to look at the control of vibration and chatter in rolling mills and grinding machines. Part two, which Florian will present, is going to be looking at downstream processes and presents findings from a research project which explores the behavior of copper presses installed on isolated foundations. So part one, control of vibration and chatter in rolling mills and grinding machines. So first of all, what is chatter? Chatter is marks on the metal strip that comes out of rolling mills. This can be visible to the naked eye, but it can also be invisible to the naked eye, and it can show up further down the process, causing issues with quality, especially at paint supply. This can happen in industries such as automotive and aerospace, but also in canning, and it can result in rejection of strip and loss of profits. Some mill vibrations can also cause gauge variation on the strip. This is where there's varying thickness along the strip, and this can also cause quality issues and rejections. We'll talk a little bit more later on about gauge variation. So there's essentially two vibration modes which can affect the mill. You have third octave resonance and fifth octave resonance. Third octave resonance is audible, and this can cause gauge variation on the strip. This is when the work rolls move into and out of the strip, causing a varying thickness. We call this gauge variation, and this causes quality issues and ultimately rejection of the roll. And then you have fifth octave resonance. This causes backup roll marking, which can later print onto the strip. This is when work rolls move into and out of the backup rolls, causing marking or chatter on the backup rolls. This chatter then prints down through the work rolls onto the strip, causing chatter on the strip. The question then is, what's the difference between the two modes? What causes them, and what can we do to resolve them? We'll talk about that now. So we'll look first at a theoretical prediction of the third and fifth octave modes of vibration. On the left-hand side here, you've got an actual mill. This is a photograph of the outside of the mill. On the top and the bottom, you've got the backup roll chocks, and in the center, you've got the work roll chocks. And the strip will pass through the center of the work rolls here. This is represented graphically here on the right-hand side. You've got 4 columns, and each column represents a different mode of vibration. So at first, you've got when the mill is at rest. There's no movement at all, so there's also no relative movement of the backup rolls or the work rolls. They're all inert. That's completely fine. You then have the first mode of vibration. This happens at around 70 Hertz. In this mode, all of the rolls, the backup and the work rolls, are moving in sync. They're moving up and down together at the same time. So there is movement of the rolls, but there's no relative movement. This means that backup rolls aren't being pressed into, and there's no relative movement between the work rolls either, so there's no gauge variation on the strip. So again, this mode's fine. Then we come to the problem modes of vibration, which are the third and fifth octave. You can see in the third octave here, represented by the red arrows, the relative movement of the rolls. The backup bottom roll and the work roll bottom roll both move together, and the top backup roll and the top work roll also both move together. However, both sets of rolls are in antiphase. What this means is as the bottom rolls move up, the top rolls move down, and as the top rolls move up, the bottom rolls move down. This means that on the strip, the work rolls are moving in and out, causing a thickness variation, a gauge variation, which causes quality issues further down the line. And this can happen at around 120 Hertz. And then we've got the fifth octave vibration. In this case, the backup rolls don't move, they're inert. However, the work rolls move in sync. This means that the work rolls move together into and out of the backup rolls and can cause marking on the backup rolls. This marking can then print back down through the work rolls onto the strip, resulting in chatter and low quality products. So we'll talk now a bit in depth about each of the types of vibration. So third octave vibration, this is an unstable resonant condition in which the magnitude increases rapidly over a short period of time. So what that means is that whenever the system's disturbed, because there's negative damping, the amplitude of the vibration increases over time instead of decreases. This can cause a lot of problems, and in the worst case scenarios can cause strip breakage in the mill. You can see this here represented by the graph on the left. Whenever there's a disturbance, the negative damping causes the amplitude of the vibration to increase over time, and that's an unstable system. The opposite of that here would be a stable system, where if it's disturbed, the positive damping would bring it back down to rest after a time. So as we said before, third octave mode of vibration will cause gauge variation. This is because the work rolls are moving in antiphase and there's a thickness difference at different parts along the strip as it moves in and out. And the frequency of the third octave mode of vibration is largely independent of speed. So the speed of the mill doesn't matter, it's a structural issue, and it's usually at around 120 or 140 Hertz. And because it's a structural issue, it's also not usually related to the presence of forced vibrations. So it's not a result of a gear or a bearing, it's a structural problem with the machine that's excited whenever the machine's running. So an example of this is a coal mill in the UK. This was a 5-stand mill, and on stand number 4, there was a structural weakness. There was movement in the rolls and in the chocks, and this was causing gauge variation on the strip. We've got an animation here that you can see on the left-hand side. In this animation, you can see the work rolls and the backup rolls. The work rolls are the 2 lines in the center, and the backup rolls are the 2 lines at the top. They're moving together in and out, or you could say panting. Now, as this is moving in and out, the strip is passing through, and the thickness is now varying on the strip. You can see here as well that there's a flexibility between the chock and the mill window, which is what's causing the movement. This was carried out using modal analysis, and that's what allowed us to view this animation. I'll talk more in detail later on about what modal analysis is and how it's carried out. But we can see from this representation very clearly that there's a lot of looseness in the machine. It's got another example here. This is a more localized third octave resonance. In this case, you can see here that the bottom backup chock was moving around inside the mill frame. When this is moving, it causes relative movement of the 2 sets of rolls, and again, gauge variation in the strip. In order to fix this, the excess clearance levels had to be restored to their original specifications. But we were able to identify that this was what was happening through modal analysis. And again, I'll talk about that in more detail later on. So that's how we can identify third octave chatter. I'll talk now briefly about what we can do to solve it. So the first thing that can be done is to use a vibration monitoring system for early detection of the chatter and to automatically slow down the mill. What this is if you have an accelerometer on the mill, you can measure the levels of vibration, and the operator can see this in real time and use these measurements to avoid speeds which are exciting the third octave resonance. As well as that, we can use modal analysis. As we just saw, this allows us to see where there's looseness in the machine, where there's excess tolerances, etc. And if we know that, we can reduce the clearances and we can add stiffness and damping to fix this. Another thing we can do is to add passive dampers. For example, a tuned mass damper could be added to the backup chocks, and I'll show an example of that in the next slide, or it can also be added on the mill frame. And finally, process parameters can also affect the third octave resonance. For example, if there's not proper lubrication at the roll bite, the levels can be changed in order to get proper lubrication, and this should improve the damping characteristics of the machine. So this is an example here. This is a tuned mass damper that's been fitted to a backup chock on stand 2 and stand 3 of a tandem mill. Once this was fitted, there was a significant improvement in the mill performance. So that was third octave resonance. I'll talk now a bit more about fifth octave resonance. As opposed to third octave resonance, which is unstable, fifth octave resonance is stable. This means that the vibration magnitude remains constant for the given operating conditions, but is amplified by the speed. So whenever the operating speed of the machine coincides with the fifth octave resonance, there's higher amplitude vibrations. As we saw before, in this case, the backup rolls are inert, they don't move, but the work rolls move up and down in sync, causing marking on the backup rolls. This marking can mean that the backup rolls need to be replaced much more quickly, so there's a reduced campaign duration. And if the marked backup rolls are left in the mill, it can cause chatter marks in the strip as it presses down through the work roll and onto the strip. This can lead to quality issues and can often lead to rejection of the strip by the customer. Fifth octave vibration is always a result of exciters. So that could be a gear, a bearing, a coupling, or it could be strip coming into the mill that's already been marked by a process downstream. The most common cause of fifth octave vibration is chatter on the rolls from the grinding machine. So chatter that's been put on the rolls from the grinding machine before it's actually got to the mill. I'll talk about that in more detail later on and about what can be done on the grinding machine to help mitigate this. So this is an example of fifth octave resonance. In this diagram, you can see here that the solid lines are the initial position of the mill. Here are the chocks for the backup rolls, the work rolls. Here's the backup rolls themselves, and in the center, you've got the work rolls. So the solid lines represent the original position, and the dashed lines represent the deformed shape. So you can see that the backup rolls, there's very little difference between the dashed lines and the solid line. In fact, they're pretty much in the same place. But for the work rolls, you can see that the dashed line has moved significantly up from the solid line originally. So the work rolls are both moving, the backup rolls are staying still. So the work rolls are moving up to and out of both of the rolls, causing marking on the backup rolls. You can see that actually on the bottom work roll, there's slightly more movement than on the top work roll. However, they're both still moving, so it's still going to cause issues on the backup rolls. We've got an animation here of this as well. So yeah, you can see here that the work rolls are moving quite significantly. The work roll chocks are moving slightly as well. And they're moving up to, in and out of both of the backup rolls. So that's fifth octave vibration. That's what it does. That's how it works. How do we solve it? So we can use vibration analysis techniques to identify the sources of force vibration. What this means is we can carry out instrumented hammer tests on the mill to get frequency spectrum. This shows us, we can use accelerometers on the mill while it's operating to see where the high amplitude vibrations are. So if we can see a high amplitude vibration at a certain frequency, we can figure out maybe this is due to a bearing, or maybe it's related to a coupling, or maybe it's related to a gear. And then once we know what the source is, or we have an idea what the source is, we can replace it, or we can run at speeds that don't excite that source. There's a number of different things we can do once we've identified what the source of the force vibration is. We can also use modal analysis to identify where excess clearances or lack of stiffness may be making the resonant behavior worse. So I'll discuss again in more detail later on what modal analysis is, but it essentially allows us to see the shape of the machine as it's deforming. So where there's looseness, where things could be tighter, where there's excess clearances. Another thing we could do is to install a permanent vibration monitoring system. I'll discuss that in more detail now, but essentially what that does is it allows the operator to see the levels of vibration on the mill in real time. So if the mill is vibrating a lot, the operator can potentially change the speeds in order to move away from those resonances and reduce the vibration. So this is an example of a vibration monitoring system that's installed in a mill pulpit. The mill operator can sit here and look at the screen, and it presents vibration levels against the speeds, and the mill operator can make decisions based on that. So I'll just go through an example now of one such case. So this is a display that the mill operator would see whenever they're looking at the vibration analysis system. In the top left, you can see here this window. This is the vibration spectrum from 0 to 1000 Hertz. And the operator can see at what frequencies there are high amplitude vibrations. On the right-hand side, we've got the readings for the 5th octave. So this is from 380 to 580 Hertz against time on the x-axis. And on the bottom left here, you've got the speeds against time. So the mill operator initially starts with a speed of around 400 meters per minute. And you can see here in real time that that's causing very high amplitude vibrations, which are above the alarm level. So what's happened is the mill operators tried to increase the speed to move away from resonance up to 515 meters per minute. But you can see here now in the vibration window that there's still high amplitude vibrations. So this change hasn't effectively moved it away from the resonance yet. Then he's increased the speed again finally to just over 600 meters per minute. And you can see here in real time that the vibration levels have dropped significantly. This is interesting because the speed's actually increased, so the mill is more productive, but the vibration levels have dropped. So the quality of the sheet should be improved as well. And this is all made possible because the mill operator can see this screen in real time as the mill is being operated. Okay, so as we mentioned before, probably the main cause of mill fifth resonance vibration is grinding chatter problems. So rolls that have come from the grinder with chatter on them into the mill and then are exciting the mill. So what can we do to solve grinder chatter? So there's two types of vibration really that are caused by a grinding machine. You have forced vibrations, which are defects in rotating equipment essentially. So that could be bearings, gears, things like that. And then you've got the chatter vibration or resonant vibration. This is the more serious of the two types because it's a result of a structural weakness in the machine. This would mean that some structural changes need to be made to the machine in order to fix it. Whereas with a forced vibration, it can often just be replacing one component. So these are some rolls coming from the grinder. The interesting thing about this photo is that both of these rolls actually have chatter on them, but you can only see one of them on the first one. You can only see chatter on one of the rolls. So you can see in this first roll here that there's quite clear horizontal chatter lines running along the length of the roll. The image on the right-hand side, there is chatter there, but it's invisible to the naked eye, so we can't see it. I'll talk a bit more later on about what we can do with invisible chatter and how it can be identified when you can't just see it, because this can cause problems in the mill even though you can't see it with the naked eye. Okay, so investigating structural problems in grinding machines. This is done through modal analysis. So we talked a bit earlier on about modal analysis and what it can do and what it can show us. So I'll explain now how it works. We use an instrumented shaker or a hammer to excite the machine, and then using accelerometers, we'll measure resonant frequencies of the machine. We would then create a 3D drawing of the machine using dedicated modal analysis software, and we would automatically read in the measurements from the accelerometer and the instrumented hammer into the software, which would create an animation showing us where there's looseness in the machine and where there's deformation. We can then analyze this animation, we can look at it, and we can use it to tell where we would need to fix in the machine, where we would need to stiffen, where we potentially need to add a tune mass damper, things like that. It's a very powerful tool. So I'll talk through now some of the examples of that and what we did to fix it. So in example 1 here, you can see the animation. On the left-hand side is the wheel head, and the wheel is obviously fixed rigidly to the wheel head. And on the right-hand side are the stocks, and the roll is sitting in the stocks. So you can see that there's quite a lot of movement between the wheel and the roll. This in and out movement can cause chatter on the roll, and it did. And that chatter on the roll will then be passed on into the mill. So by performing modal analysis, we were able to see what the issue was. The headstock and the wheel head and the headstock were both moving, but they were moving because they were rigidly fixed to the bed, which itself was deforming, as you can see here in the video. The bed's moving up and down, and that's because it wasn't rigidly fixed to the foundation. There was too much looseness. So to solve this, additional bolts were added to the bed. It was tightened to the foundation, and the stiffness was increased. That meant that the bed moved around less. Because the bed was moving around less, the wheel head and the headstock, which were rigidly fixed to it, were also moving around less, and there was less relative movement between the wheel and the roll. So this is another example. In this case, the wheel head was moving around the slide. You can see very clearly here it's moving up and down. There should be some movement between the wheel head and the slide, but nowhere near this much. The wheel head's moving in and out of the roll, the wheel's moving in and out in the roll, and that causes marking on the roll and chatter. So in this case, there was a looseness in the interface between the wheel head and the slide, and this could be fixed by stiffening the interface. And that would cause less movement between the wheel head and its slide, and therefore less movement between the wheel and the roll. And we were able to identify this using modal analysis. The third example here, this is from the other side view. So in this case, there was torsional distortion of the workside bed. You can see in this animation here that the bed's twisting. In this case, that meant that the roll was also moving around a lot and relative to the wheel, again causing chatter on the roll. In this case, we needed to stiffen the workside bed structure, and that was done by adding machine mounts under the end of the work roll here. So modal analysis allowed us to see where the problem was very easily, and then we were able to use an easy solution to fix what was quite a big problem. And the final example here was flexibility in the front bearings. So there is a degree of freedom here in grinding machines. The wheel head should be able to move slightly so that we can create convex and concave rolls, but not by this much at all. There was far too much looseness. It was moving in and out and causing chatter on the rolls. So in an example like this, what we can do is we can use a tune mass damper at the back here to reduce the amplitude of the vibrations to stop the wheel head moving about so much, and therefore stop the chatter on the rolls. I'll show an example of that now. So this is actually, in this case, this is a tune mass damper that was fitted at the back of the wheel head. This reduced the amplitude of the vibrations and added damping to the overall system, and meant that there was much less relative movement between the wheel and the roll. And that was a relatively easy fix that we knew to do because of modal analysis. So in order to verify that this worked, we wanted to compare the frequency spectrum before and after the tune mass damper was installed. So you can see here, this red line represents the system before, the resonance before the damper was installed. We've got a very sharp peak here at 22 Hertz. The sharp peak shows us that there's low damping in the system. Now, once the damper was added, you can see that this peak has been reduced significantly, completely smoothed out, and that means that there's good damping properties and the vibration is gone. We completely eradicated the problem that was caused by the looseness in the machine by adding the tune mass damper. And you can see here the amplitude of the vibration at resonance reduced from around 55 or 60 all the way down. So there was about a 5-fold reduction there. And that completely solved the issue by adding the tune mask damper. Okay, so as I mentioned before, not all chatter is visible to the naked eye. Sometimes it is. You can look at the roll and you can see it very clearly. The operator can tell, but sometimes it's completely invisible. You've got an example of this here on the left-hand side. This roll actually has chatter on it, but you would never be able to tell by looking at it. So Farrat have a system called Chatter Detect that allow us to measure chatter on the roll using a capacitive sensor. It's a non-contact capacitive sensor, and what it does is the operator will turn the roll slowly around with the capacitive sensor placed near the roll. The capacitive sensor will be able to measure the varying depths of the roll, and it will feed those readings into the Chatter Detect software, which will give the grinder operator information about the roll and the chatter properties of it. So this is an example of a display that would be given to the grinder operator. In the top window here, this is the circumference of the roll represented around the x-axis. So it's the circumference flattened out so that we can easily analyze it. And the waviness represents the different depths of the roll as the capacitive sensors read it in. So how Chatter Detect works is it separates the circumference into 10 sections and then takes readings for each of those 10 sections and splits them into these bars here. So the operator sets a threshold initially. This is a threshold for the depth of the markings on the roll. If the marking readings for each section exceed that threshold, they come up in red. So you can see the 4 bars here in red. These have all exceeded the depth of the threshold. As well as that, it also gives us the pitch here. So we can see that there's a chatter pitch of 1.04 for section 1, and that chatter exceeds the depth of the threshold of the marking. You then have 0.92, 0.88, and 0.87 for sections 4, 5, and 6. These green bars here have all passed. So these 6 sections have all passed. The depth of the markings was less than the threshold. But because we've got 4 that were exceeding the threshold, the grinder operator would know that this roll has chatter on it. And what they would usually do then is they would refinish the roll to remove the chatter. The grinder operator is looking for all 10 of these sections to be green. If he sees that they're green, he knows that the roll is acceptable, there's no chatter, and he can pass it on. We also have a tool in Chatter Detect here that allows the grinder operator to see what the marking frequency would be. So you would enter the roll speed here, and Chatter Detect would automatically calculate the marking frequency. And this can tell the operator potentially what the source of the vibration is that could be causing the marking. And it can also tell them potential speeds to avoid in order to avoid exciting those resonances. So here we have a case that would pass. You can see here that the line is much smoother, which is what we want. It's nearly flat. You can see as well that all 10 of the sections are green, meaning that they've all passed the threshold, which is set by the grinder operator. So the grinder can look at this window now, and he can know that he can send the roll to the mill with confidence that there's no chatter on it, and it's not going to cause any problems in the mill. Okay, so those were all post-process ways of analyzing the grinding machine. But Chatter Detect also has some in-process vibration monitoring tools, which allows the grinder to see what's going on as the roll is being ground. These are displays of the vibration levels. You can see here the red line is an alarm level. The x-axis here is time, and the y-axis is the amplitude of the vibrations. So you can see here initially, the top chart is the wheel head and the bottom chart is the stock. You can see that the vibrations initially are just on the alarm level, but then the grinder has obviously changed something and the vibration levels have exceeded the alarm level significantly. So the grinder's then tried to change something again. He's brought the vibration levels down slightly, but they're still above the alarm level. So using this tool, the grinder can in real time see what's happening on the mill or on the grinder and see what the vibration levels are like. and he can make changes to the speeds and the feeds in order to bring the vibration levels below the alarm. There's also a tool in Chatter Detect which allows the the grinder operator to see what the vibration levels are like at different frequencies. So using this tool, we can see here that there's high levels of vibration at around 75 Hertz. The grinder can also drag these yellow lines along the spectrum. So if he moves the yellow line along the 75 Hertz, Chatter Detect will tell him what marking pitch we would expect to see on the roll because of that vibration, and it performs those calculations using the diameter, which the grinder enters here, and the speed, which the grinder enters here. So if Chatter Detect's telling the grinding operator that they might expect to see, for example, 0.58 inches due to the 75 Hertz vibration, if the grinder then runs Chatter Detect and it measures those chatter marks, he can know that this frequency is what was causing those chatter marks, and he can potentially do things to prevent that frequency from causing the marks again and mitigate the issue. Okay, so that's my presentation done, my portion of the presentation done. I'll now hand it over to my colleague Florian for his.
Thank you, Jacob. Right, I'll share the presentation directly to you. Right, it's uploading now. Right, I believe you can all see the first slide now.
Yeah, I can see that now, Florian, thanks.
Right, perfect. So hello everyone, I'm Florian Cabaret, also working for Farrat as applications engineer in the industrial department, and today I'm going to present you the effects and benefits of isolated foundations on impact machinery vibration with a special focus on presses in the canning industry, which use the aluminium rolls just mentioned by Jacob. So this will illustrate the fact that even though big work has already been done to make sure the good quality aluminium rolls are used, the battle against vibrations and disturbances is not over yet, and there's still a lot to be done to produce good quality products at maximum productivity and in a safe environment. So in this presentation, we'll examine the effects of presses in different production facilities, and we'll explore some of the solutions used to properly mitigate these effects. So first, we'll define what impact machinery is. Secondly, we'll present practical techniques to isolate this type of machinery and show what a typical Farrat anti-vibration system looks like. And then we'll explore ways to measure vibrations generated by presses and show how this procedure has been used to undertake vibration surveys on similar presses from different factories. Finally, practical examples will be presented to illustrate the potential effects vibration can have on the overall productivity of the machines and on nearby sensitive machinery as well. So impact machinery is described as machinery that generates an impact, such as high force or shock, over a very short period of time. This type of force is typically generated by industrial machines, such as forges or presses. We'll focus on copper press in this presentation, which are used to produce aluminium cans. They use rolls of aluminium sheeting, hopefully of perfect quality thanks to Youssef and Jacob's work. And they perform two operations. They firstly punch out simple discs and then form them into cylindrical cups. So these actions generate vertical excitations that can be considered as shocks, repeated at frequencies determined by the speed of the machine. And the shocks produced can then alter the proper functioning of the installation, systems and components, eventually reducing the machine productivity, damage the building, and generate waves and noises propagating in the environment. Considering all these effects, it's therefore necessary to minimize the transmission of the shock forces and reduce the vibration level to the surrounding environment. And this is where Farrat expertise plays a critical role in the isolation of this type of machinery by designing and supplying bespoke anti-vibration systems. So the first thing that comes to mind is to use resilient elements that will act as isolators. So isolators are flexible elements used to attenuate the transmission of shock or vibration from the equipment to the structure. The isolator selection is done based on different factors, such as the mass and speed of the machine, level of isolation required, etc. And what's usually encouraged in these types of applications is to add mass to the system. For this, a concrete inertial block is poured on top of the isolators so they can achieve a certain level of compression, improving their performance in terms of shock absorption. The inertial block also provides more stability to the structure. It reduces the rocking of the machine, and as a result of increased stiffness and lower center of gravity, it maintains alignment during changes in static and dynamic loads. This image shows a typical industrial machine installed on an isolated foundation made of an inertial block supported by isolators. And this photo presents how a typical Farrat anti-vibration system looks like before the concrete foundation is poured within the pit. Cork composite strips are used on top of the side walls to add lateral stiffness and prevent rocking of the foundation and increase its stability. Void former is also used to support these strips on the walls and ensure a flat surface on the base to distribute equally the loads from the inertial block and the machine onto the elastomeric rubber pads, which absorb shocks produced by the machine to isolate the system. As part of Farrat's research program, different vibration surveys were undertaken in some factories to determine the performance of isolated foundations supporting copper press systems. So this first chart presents the vertical acceleration measured on the feet of 4 different presses from 3 factories. The second chart shows the vibration levels recorded on the isolated foundations supporting those same machines in dark blue, and on the surrounding factory floor in lighter blue. So let's now analyze the obtained results. So factory 1 shows a vibration level measured at the feet of the machine, very typical for a copper press, with an acceleration of almost 8 meters per second square. However, no reduction can be observed from the inertia block supporting the press to the factory floor. So this can be explained by the isolation system supplied by a competitor which might have gone for a wrong design or product, but also some bridging connections have been observed with one column in particular rigidly bolted to both the inertia block and the surrounding factory floor, helping vibration getting transferred around. So this specific example will be developed in one of the next screen, showing how the poor isolation performance has affected the sensitive machine positioned nearby within the factory. Factory 2 presents 2 models of presses. First one is a DAC 165, and although being 20 tons heavier than the other DAC 150, it was also running at higher speed, 130 against 150, 15 RPM, They both present similar level of accelerations, highlighting the efficiency of the DAC 165 internal balancing system. It's interesting to notice that although the DAC 165 was running faster than the DAC 150, the accelerations recorded on its foundation and surrounding floor were lower than the DAC 150s. So this demonstrates the remarkable properties of Farrat elastomeric pads, more performant when subject to faster machine speed and achieving an overall reduction percentage of 99% from the machine feed to the floor. Factory 3 has got a DAC 165 press, which has been measured at two speeds of 158 and 225 RPM. This increase of 41% in machine cadence results in a vibration increase of 44% in terms of vertical acceleration measured at the feet of the machine. This tends to show the linear relation between the machine speed and its internal level of vibration generated. But the increase of vibration at faster speed is also reflected on the foundation. However, the acceleration measured on the surrounding factory floor is similar for both speeds, and the overall percentage reduction is still 99%. So again, this result demonstrates that the pads used under the inertia block can keep a very low level of vibration transmission, even when subject to higher level of energy. Once again, highlighting the excellent mechanical behavior of rubber products. Another real-world case study can also be presented to highlight the performance of Farrat isolated foundation designs. In this instance, Canning Factory was having issues with a copper press, generating excessive vibrations that could be perceived by neighbored building that were placed at a distance of 70 meters from the machine. A study performed by a consultancy specializing in vibration and structural dynamics concluded that in order for this press to be properly isolated, a natural frequency of 1.25 Hz should be achieved by the isolation system. And based on this recommendation, the factory went for springs elements and visco dampers, as shown in this photo, supplied by one of our competitors. It was reported that the surrounding buildings stopped perceiving vibrations generated by the machine after installation of this product. However, at the same time, it was also observed that the springs, together with the foundation and machine installed on them, started to present unexpected high movement. As a result, premature wear and increased spoilage were caused, reducing the overall productivity of the plant. Farrat was therefore asked to provide a solution that would reduce the excessive movement of the press while maintaining a quiet environment for the neighbors' buildings. So the challenge for us was to stiffen the overall system while preventing excessive vibrations being transferred around. In order to solve both parts of the equation, the engineering team worked on bespoke bearings made of a steel base and 2 layers of natural rubber, as presented in this picture. A vibration survey has been carried out to measure vibration before and after replacement of the spring packs to assess the efficiency of the offered solution. The main result of this survey is presented in this plot, showing the vertical accelerations measured before replacement with the blue curves and after installation of Farrat isolation system with the orange curves. Vibrations measured at the feet of the machine are shown on top, on the inertia block in the middle, and on the surrounding factory floor at the bottom. A vibration reduction definitely appears on each part of the system. It's particularly clear at the operational speed of the press, slightly below 2 Hz. This is the frequency of interest, since it's where the machine as a whole is likely to be moving and rocking, and these are the vibrations that can be perceived and impact the process quality. So it has to be noted that these results were observed at all measured operational machine speeds between 110 and 170 RPM. So these results demonstrate that the client's requirements have been met. Farrat isolation solution has significantly lowered the movement of the machine while still maintaining a quiet environment for the neighbors' buildings. So this proves the efficiency of Farrat rubber isolation system for this type of application where bespoke design solutions are needed to solve complex engineering challenges. On the other hand, springs with visco dampers have proven unsuitable because of their very low natural frequency. In this case, in this particular application, dangerously close to the disturbing frequencies generated by presses and increasing the risk of facing resonance issues. Now that we've seen the impact of vibration from poorly isolated presses, let's focus on one particular example from Factory 1, which highlights one of the potential consequences excessive vibration transmission can create. A direct laser exposure system using a direct laser engraving method is located in an office close to the production lines of Factory 1 and 30 meters away from the press described previously. This machine is used to produce the masks needed to decorate the various types of cans produced within this factory. So it requires a very high level of precision and stability. It was reported by the line manager that this precision machine was subjected to excessive vibrations, altering its process quality. As a reminder, this is the chart presenting the vertical acceleration measured on the inertia block and surrounding factory floor, showing the poor performance of the isolated foundation supporting the press. In order to determine the influence of the press, we've measured the vibrations on the printer in 3 different directions while the machine was on and off. The results are presented in this plot for X on top, Y in the middle, and Z at the bottom directions. So the orange curves were obtained when the press was off, while the blue curves were obtained with the machine running at its normal operational speed. So the first few peaks, all located below 20 Hz, were generated by other machines, only positioned 7 meters away from the printer, but we can clearly see a difference in all directions between 20 and 50 Hz, presenting the influence of the copper press, although located 30 meters away from the printer. So this problem was solved by inserting Farrat isolation pads made of polyurethane foam below the printer. This highlights the importance of isolating properly heavy impact machinery generating important level of energy. In conclusion, we've seen that impact machinery produces shocks, generating huge amount of energy in a very short period of time. This energy has to be absorbed by means of an interface between the machine and the factory floor to avoid or at least reduce the transmission of excessive level of vibration to the surroundings. A typical way to isolate this type of machine is to insert an anti-vibration system below, made of an inertia block supported by isolators. The measurements performed on different presses have highlighted the very important isolation performance Farrat anti-vibration systems can provide to the industry, with overall vibration reductions of 99% from the machines to the floors. The results also showed these performances were even improved with the increased machine speeds, which has now become crucial considering the very high cadences and production rate required by the industry. Finally, 2 examples have been presented showing the importance of properly isolating impact machinery. By doing so, effects on nearby sensitive machinery are highly reduced, allowing a freer positioning of the various machines in factories. Appropriate anti-vibration system design is also required, since we've also proven that industrial machinery subject to lower vibration will increase its productivity. Lastly, it's worth mentioning that vibration reduction will also reduce risk to the health and safety of workers, usually exposed to high level of whole body vibration. Right, thank you for your attention. I hope you found it useful. If you have any question, please feel free to ask.
Thank you, gentlemen. Much appreciated. There are not. I don't see any questions in the chat. Does anyone have any questions? If so, either put them in the chat or put your hand up. I'm just catching up on that. Alistair, do you have a question? Do you want to unmute yourself and fire away?
Yeah. So, Alistair Clark, working for Ansaldo, who make gas turbines, and I'm quite involved in structural dynamic calculations. Do you hear me okay?
Yeah, perfectly.
Okay, good. You showed the laser device, which was improved. Did it also improve the vibration from the other sources?
So in this case, the main disturbance was the copper press. As I mentioned, there were also some other machines only located 7 meters away from the printer.
Yeah.
So that couldn't be avoided because the location wasn't ideal. So what we could do, though, is limiting the influence from the press. And this apparently solved their problem.
Okay.
I think because it's in the frequency range of that, just of what's disturbing it.
Yeah, exactly. So any type of isolation solution that we provide would be targeting a certain frequency, the main disturbance, basically.
Yeah.
And in this case, it would appear that the main one was coming from the press.
Okay, thank you.
Yeah.
Anybody else?
Hi, Florian. Hi, Oliver. It's Niklas here. Am I okay to ask?
Hi, Niklas.
Hi.
Yeah. So thanks for the presentation. Really, I wanted to ask on the presses. We do get these jobs sometimes of vibration, sort of assessment of potential press being introduced in a sensitive premises or near a sensitive building. So what part of the design would you come in? Would it be, let's say, we do the assessment and we derive what specification, natural frequency, etc., and then you would design the right inertial block, etc., or would you also come ahead of that, maybe understanding or taking any measurements, things like that?
So the copper presses come as a finished product, and we don't have any influence on their dynamic themselves. So we just consider the machine as a whole that needs to be isolated. So we have an influence on, as you said, on the inertia block and on the lateral and the bottom isolation. Now, in the future, and this is what we're trying to build through different research projects, the objective would be to be able to characterize the dynamics of any type of machine, and also work on individual characterization on any sub-elements of the global system to be able to know how, or to predict at least how the global coupled assembly would behave. So we'd be able to basically modify the different properties and to find optimum solutions based on particular vibration sources.
Yeah.
So this could have later on an influence on the dimensions of the inertia block, on the properties of the isolators to be used as well to meet any type of client requirements.
Okay. Yeah. And does that, with elastomeric isolators, you'd have a range of movement beyond which the rubber or neoprene would stiffen up. Does that cause any issue, or do you have like bump stops or something like that to limit that movement?
No, so we always anticipate the dynamic. So the static load is easy to get from the mass of the inertia block and the machine. We also try to anticipate the dynamic loads generated by the process of the machine. And based on that, we always try to specify material and products that can bear basically these loads, and that would allow them to achieve an optimum level of compression in order for them to give their best properties, basically in terms of vibration isolation. So we always try to keep a strain percentage below 20 Hertz, considering that the ideal level of strain for rubber products would be located between 10 and 15% of strain.
Okay, thank you.
Thank you.
Troy, you had your hand up. Yeah, do you want to fire away?
Yeah, sure. Thank you. And thanks for the information, you know, on the chatter and the third octave, fifth octave. How do you distinguish what I'll say is mechanical displacement generally being transferred through the drivetrain to the work rolls and then to the sheet? It's something that we see in the metal being produced, but you don't necessarily have many signals that you have a problem at the mill. So it's imprinted in the sheet, and a lot of times you have to see it after even stoning the surface to see this underlining chatter that's being produced. A lot of times it's from tremendous number of different sources, but it's kind of hard to pinpoint. How do you characterize that type of chatter?
Hi, Troy. Thanks for this. Yeah, what it is basically what we do is you need to correlate between what you see on the strip and then the frequencies that you're measuring. So that's how we proceed. You correlate, you measure. If you have a problem, you measure the pitch accurately, and then you try to correlate with which frequency may cause this.
Yes, but I was just wondering, like, when you start chatter on the first few slides, you said there's two forms of chatter: fifth octave, third octave.
That's correct.
This type of chatter, I don't think is third octave or fifth octave. It's some sort of mechanic. I agree that how you find it is you look at the frequency and you measure everything and you figure out where that source is coming from. I'm just wondering, what do you call that type of chatter that is being mechanically induced, but it is not third or fifth?
Right. Okay. Yeah. Okay. So what you're probably talking about here, Troy, is force vibration somewhere within the middle. Okay, you've got rotating components, and then if there is a defect of some sort, that will generate a frequency. And I agree, it may not be exciting one of the mill resonances, but it has got enough energy to affect the process. Is that what you're asking, Troy?
Yes, that's exactly right.
Yeah.
Thank you.
Yeah. So
it might be helpful on a presentation to include that as a third type, because when people say chatter, it's not always just the vibration aspect, but this mechanical displacement or this forcing function, like you're saying. Yes.
That's correct, but you will be surprised that without any amplification from mill resonances, I see it very difficult to see how it can mark the strip. So there will be an exciter, but it's always two sides to the equation here. You've got the exciter and you've got the mill response. Okay, and both of them usually contribute. So you've got an exciter which excites a mill resonance, and then the end effect is marks on the strip.
Okay, very good. Thank you.
Yeah, okay. You're welcome.
Okay, I think there's no, I can't see any other questions there. So
there's a question in the chat
on sorry, analysis, yes, okay.
Yeah, on our analysis on mills. So Yusuf, the question this is from Peter. So Yusuf just helped us in answering this. It says, has any analysis been done on 6 high mills? Also, does the frequency vary depending on the mill stiffness? Yeah,
yes, we have worked on 6 high mills. The we haven't done any modal analysis, but certainly the behavior of the 6 high mill is very similar to 4 high mills, and there will be resonances responding, as I was telling Troy before. There will be resonances of the mill responding to non-exciters. And as my colleague Jacob mentioned before, one of the most common exciter is grinder chatter. So grinder chatter, often what we see is grinder chatter on the intermediate rolls, as well as the work rolls and also the backup rolls. Okay, and these will, this will excite the mill and causes chatter on the strip. Okay, so the behavior is very similar. I mean, an investigation on the 6 high mill, we would proceed exactly the same as if we were on the 4 high, which is identifying first what are the exciters, okay, and then see whether there is any contribution from resonances, and then take it from there then.
Is that okay, Peter? Happy with that?
Yes, thank you. There's also, sorry, a second part. Does the frequency vary depending on the mill stiffness?
That's correct. Yeah, of course. Yeah. There will be. I mean, the stiffness affects the resonances. So rolling loads will affect the roll balance, rolling load. All these will stiffen up the mill and changes the frequencies. So exciters will be the resonances will move. Not very much, but there will be at least 100 hertz, changes in frequency as a function of rolling loads and also balance force.
Okay, thank you.
Okay.
Okay, everybody, thank you. We're slightly over time, but I think it was worthwhile, hopefully. So thank you, gentlemen, for the presentations, and thank you for all the guests that have taken the time to listen in and put questions in. Hope it's of interest, hope it's of use. And yes, we'll pick it up and try and keep having events going forward for the months and years ahead. So thank you. I wish you all a nice evening, and speak to you soon.